Cheat.
Oops.
I was waiting for this.
I figured you were.
Dr. Joe, what's the probability of you enjoying miracle notes?
0. It's true.
That was wrong. I heard people were talking about I feel like I shouldn't have been required to take it.
Well, you took it, so you're.
And I already suffered through counting, so like everyone else should have to suffer through it.
It just means you had to take a different class.
Yeah, they're just gonna.
You just would have had to have taken a different class.
Could be as bad as miracle.
Oh, there's things that could be worse.
Like what?
Non-math classes?
Some non-math classes are actually nice, though. I'm taking haiku, and that's pretty nice.
I heard you and Matt like had a big something about dishes.
Oh,
All right, any questions before we get going?
Sorry, Matt.
All right, so last time we finished up talking about moment generating functions. So let's do one more example with that before we talk about a couple of different distributions, which you may have noticed are on your homework.
What's on our homework?
Grace, you
I didn't hear what he said.
literally there.
Oh my
You
God.
literally asked.
You asked me the question earlier
About
today.
what?
The negative binomial and geometric distribution.
Oh.
Really?
That's all I needed to know. I just did not hear what you said.
Good grief, Grace. What am I going to do with you?
Oh. What?
All right, 27.8 gives you the moment generating function for a random variable, and it asks you to find the variance. Moment generating function is section 2.5. Huh.
I thought it was later. That's a good one.
Marshall.
What is it?
Oops.
Sorry.
The variance. Well,
It better be.
I got some. But I also don't do derivatives 20%.
All right, in terms of the moment generating function, what do we have to do? I wrote down our formula that we typically use for finding the variance, but in terms of the moment generating function, what do we have to do? Okay, so how do we find expected value of x squared using moment generating function? Take the second derivative and evaluate it at 0. And then for the expected value of x?
The first derivative.
You sneeze really loudly and take the first derivative. Okay. So over here, when you want to find the mean, I just wrote this off to the side, just kind of remind you. The mean is m prime of 0. The variance is m double prime of 0 minus m prime of 0 squared. In terms of the moment generating function, that's how you find those. Now remember again, those first two properties that I wrote down, the first one is just the definition of moment generating function. We define the moment generating function in that fashion because when we take the derivatives, we get the moments. We take the derivatives and evaluate it at 0, we get the moments because again, we're differentiating with respect to t, treating x as a constant. The first derivative here would be x, e to the tx. When you put in 0 for t, you just get the expected value of x. And so on down the line. That's why we call it moment generating function. All right. So before we do anything else, I need to take a couple of derivatives, right? Right, this is a power. When I take the derivative, I'm going to need to bring the power down in front, make it a -2, and then bring out the derivative on the inside, right? Yep. So I should get 0.16 e to the t, and then times 1 minus 0.2 e to the t to the -2. All right, because I'll get a negative 0.8, and a negative 0.2 e to the t will pop out when I take the derivative of the inside. So you get a positive 0.16? I don't. You bring the negative down in front, right? Make it a -2, and then I got to take the derivative of the inside, which is negative 0.2 e to the t.
Oh, I was about to say, I was like, we're about to get a lot of zeros there. Okay, yeah,
Okay. And then when I take the second derivative now, though, what am I going to have to use? I got to use a, well, I got to use a chain rule, but what else do I have to use? Got a product of two things, right? So derivative of the first will just be itself. And the derivative of the second will be a similar derivative to what we just did. I got to bring the -2 down in front, decrease the power by 1, multiply by the derivative of the inside. So what do we get? 0.4 times 1 minus 0.2 e to the t to the -3? Probably seeing a little bit more now why calculus is a prereq. Wait till we start doing integrals. You can see why calc 2 is a prereq. What's calculus?
I've never heard of
The calculus, yeah. All right, so now to find these values that we need to plug in 0 for t. Oh, so what do we get for the first one? So we'll get 0.16, e to the t will be 1. So then that'll be times 0.8 to the -2. And then the second part will be 0.16 times 0.4 times 0.8 to the -3. And then I got to subtract off what I get when I put in 0 into the first derivative and square it. So that'll be 0.16 times 0.8 to the -2 squared. I'm just plugging in 0 for t, and then writing out what it'd have to be. That looks like a nice task for a calculator. Yeah, it's subtraction out in front because I'm subtracting off the mean squared. Yeah, it's still attached to this. I just ran it. This part right here is this minus part here. Maybe I'll help. Or maybe it'll be worse. That's that part. And this is that part. That might be worse, but it's better than just scribbling all over everything. 5/16. 5/16? Is that what you got? Anybody else get 5/16? Of course you don't want to do that. Anybody else put in their calculator?
I'll tell you.
What if they want to?
No, I just redid my derivative. I put it back to the -2, so I didn't quite
At least I started with the right letter.
Yeah. Honestly, the word still hasn't come from the other one. Quotient. That's it.
Why'd you tell her? I was waiting for her to be about 25 minutes from now and say, quotient, bro.
That would be really funny.
By that time, I would.
That's what I was waiting for.
I would do that.
Anybody else confirm the 5/16 diagnosis?
I mean, I probably
That's how I'm
looking at it.
It's 5/16. Hey, I got a confirmation. I'll take 5/16. Got independent confirmation, unless you just stole your calculator.
It's not a multiple choice one, so
Yeah, oh, hey, I got 3 now.
I'll tell you.
Did you
I
get
got
it?
5/16, but I didn't.
Ashley just quit. Ashley quit. I get it. I can tell with a smirk on your face, you just stopped. All right. Besides derivative issues, perhaps, does the concept make sense what we did? Just take the derivatives, plug in the 0, get your answer?
Yes.
Yes. Good. Okay. All right.
Do you like a crazy color?
You want a crazy colored one?
Yeah.
Like, how about the stars? Like
Yeah, the star one. Yeah.
the star one?
5, 6, 6.
Okay. Why not? All right. It's going to be very colorful.
That's really like that.
All right. So let's see if we can do some of these that involve other distributions besides the binomial. So let's look at the ones that say the exercise, the lesson 20 handout that I gave last time. Which also says negative binomial distribution. 20. So exercise 20.1 says that 10% of all new businesses fail within 1 year. They're going to analyze businesses. They're going to analyze records of new businesses until they find the first one that failed. They're going to stop analyzing businesses until they find the first one that fails. It says let X be the total number of businesses examined with it until they find the first one. What's the probability? What's the probability distribution function? The probability mass function for X. All right. So they're going to go into these records. They're going to pull out a record and say, "Oh, I got one that failed. I quit." Or they got one that didn't fail, and so they go find another one. Pull out a second, and they do the same analysis. And as soon as they find one that failed, they're going to quit. Okay? So what are the possible numbers of records that you would have to look at until you find the first one? What are your possibilities for numbers that you have, the total number of records you have to look at? So you need discrete numbers starting at 1. Cool. Yeah, X could be 1. You could get lucky, pull out the first one, and notice that it failed, right? And stop. Or the first one didn't fail and the second one did. Or the first 2 didn't fail, the third one did, right? And so on down the line. So our support here, I'm introducing the new distribution with this particular example. So the support for this random variable is the color annoying or is it fun?
It's fun.
It's fun? Okay. If it's annoying, I'll stop you. All I do is I'm writing and I hear snickers in the background.
It was just really funny, just like because we haven't.
It looks like crayon, the 20.1.
And my handwriting, so.
Yeah.
It looks like a 2-year-old's writing this. So.
Yeah, well, it happens. Well, you can change it over to highlighter mode too, and then highlight some stuff if you want. That's just weird. I thought it was weird. Anyway, all right. So the support is 1, 2, 3, and so on. So this, remember, this is the first time that you make the observation, right? So notice again, we've got something that looks like a Bernoulli trial, right? You either see the business failed or it didn't. But we're not counting, we're not taking a random sample and counting how many in the sample had failed, right? We're going to keep taking records until we hit the first one and then we stop. That's not binomial, right? So we still have this Bernoulli trial, but just because it's a Bernoulli trial doesn't mean that it's a Bernoulli random variable. Okay? Remember, Bernoulli random variable says you're going to take a sequence of trials and count how many successes happened, right? In this case, we're going to keep doing trials over and over and over again until we get the first success, and then we're just going to stop. So at any given time, there's only one success out of that sequence of trials. Right? That's the difference. Okay? But our support's the same. We still have this probability of success idea. And in this case, it's 0.1, right? Success here is finding a business that failed. I told you sometimes the idea of success is kind of weird, but it's what we're looking for, isn't it? They're going to keep searching records until they find a business that failed. So you want probability of success in this case is 0.1. Okay? same idea. We still have Bernoulli trials, right? But it's just we're going to stop when we hit that first, pardon me, when we hit that first success. All right, so just to think about how this goes along, what would be the probability of success, or probability of, sorry, not of success, probability that x is equal to 1, sorry to say, in this case. What would be the probability that x is 1? What does that mean? The first one you checked failed, right? So what would that be in this case? 0.1, right? What would be the probability that x is 2? What would have to happen for x to be 2? The first one was fine, and then the second one failed. So what's the probability the first one didn't fail? 0.9, and then did fail 0.1. What should I do with those two numbers? Multiply them, right? And I'm not going to simplify it right this second. We're looking for a pattern. How about the probability that x is 3? Okay, the first two didn't fail, the third one did, right? So what's that probability going to look like? Okay. Sometimes it changes to that lighter green. It looks like I'm running out of ink. That's what I think. All right, this 0.1 over here is suspect.
You have to remember shaking it.
Oh, okay. All right. What if we want the probability that capital X equals little x? Well, what has to happen? X minus 1 fail, or excuse me, x minus 1 didn't fail, and then the last one did, right? So what's the formula going to look like? 0.9 to the x minus 1 times 0.1, right? This will be our f of x. All right, so we had this for 1, 2, 3, and so on down the line. Now, this doesn't look like any of the answers they gave us, but can you change can you change anything about what we did to make it look like one of the answers? Maybe?
Probably. Yeah.
Which one does it look like? It looks like A, doesn't it? Just been shifted, right? Instead of x going 1, 2, 3, and so on, and subtracting 1 from the exponent, they just said go from x being 0, 1, 2, and so on, and just make it x, right? So it's just they just shifted it, and it's the same thing. So this would be A. All right, but let's talk a little bit more about the form of this particular thing. All right, so just in general, let's say that, suppose that x counts the number of Bernoulli trials. Why do I always put an extra I in Bernoulli? I don't know why. Until the first success occurs. Remember Bernoulli trials? There's important characteristics of them. They're independent and identical, and only two possible outcomes, right? The outcome of one trial does not influence the outcome of any other trial. It's the same thing you're doing over and over and over again, so like flipping a coin over and over again, rolling a die over and over again, so on down the line. Independent and identical. right? And only two possible outcomes, success or failure. Okay? So this is what's an example of a geometric distribution. So if you're counting number of trials until the first success happens, that's a geometric distribution. The PMF for X, keep forgetting to lay this one. The PMF for X is, well, we would have, how did we get this 0.9 to the x minus 1 times the 0.1? What did we do? So what does the x minus 1 represent? Failures, right? The number of failures in a row, right? Until the success, right? So if we use P for the probability of success, like we do for our binomial, what would the 0.9 be in terms of P? The 1 minus P, right? The other way around, correct? So for the PMF then, this would be 1 minus P to the x minus 1 times P. And then our support here would be 1, 2, 3, and so on. We should be able to check that this really is a PMF. I mean, we argued that it should be a PMF, right? This should exhaust all the possibilities. But to check that it is indeed a PMF, what should I do to check it? You can sum it up and it has to be 1, right? So just as a check to make sure this really is a PMF, we would have the sum from x equals 1 to infinity of 1 minus p to the x minus 1 times p, right? This p here on the end have anything to do with x? No, what can I do with it then? Pull it out? Yeah, good. My geometric series formula, Morgan was asking about it earlier, so I have actually conveniently written her on the board. That was fun. Lucky. Okay? So if I start at 0 and have my common ratio raised to the just the x power, I get 1 over 1 minus r. Is that what I have in this case, essentially? Yeah, because I'm subtracting off 1 here, right? I can re-index this to start at 0 and make this just an x, right? So we should get p times 1 over 1 minus p. Something's not right. Oh, no, I'm supposed to get 1. Never mind. I was thinking something else. My bad. I got worried for a minute. Yeah. All right. Couldn't tell. All right. Shoo. Never let them see us wet, right? What does the bottom simplify to? P, and then multiply by P, I should get 1. Should get 1. That's what I said. 1, yeah. Yeah, P over P, yeah. Should be 1. All right, which is what we wanted, isn't it? All right. Questions on that part at all? All right, so let's think about some things we might want to know about the geometric distribution. Well, we might want to know what its mean is. We might want to know what its variance is. We might want to know what its moment generating function is, right? Actually, if we do the moment generating function first, we can figure out the other ones because we know we can do the mean and the variance from moment generating function. But this is an instructive exercise. Let's do the mean by first principles for how the mean is defined. Remember, mean is expected value of x, right? So I would take the PMF and multiply it by x. Now I know several of you are in Calc 3, and several of you just had a test over power series. I don't know, you know what I'm talking about? Okay, fine. Be that way. Don't know what I'm talking about then. That sum and looks like what kind of calculus thing happened? What does it look like? Thinking about, in particular, this series, what does the inside of that sum and look like? It's not quite geometric because I got an X in front, right? What does it look like I did to this series to get to that one? Okay, what else? What other calculus kind of thing could I do to get the same idea? I took the derivative, right? It brings the X down in front and decreases the power by 1. Does this look like something you did in Calc 3?
Oh, yeah.
Oh, I hope so. All right. This looks like the derivative of that. This looks like the derivative of that series, correct? Well, if I differentiate the series, what do I do to the other side? Differentiate it, right? Same idea, correct? Right? So this should be the series for 1 over 1 minus r quantity squared, right? So this is going to be p times 1 over the quantity 1 minus p squared. Because if you differentiate, this is differentiating with respect to r, right? This is a little bit different than what you kind of, because you had the x here and the n here or something, right? I've got it flipped, right? I'm treating the x like it's the n and differentiating with respect to r. So this would say the sum from x equals 1 to infinity of x r to the x minus 1 is 1 over 1 minus r squared. No, I don't. Derivative of your negative 1 pops down in front, and then the derivative of the inside is another negative. Yeah, that's why. Yep, there's no negative there. Better not be, because otherwise I'm going to get a negative answer. That's bad. What is this going to simplify to? P over p squared, so I get 1 over p. All right, let's see if that makes sense. I roll a die over and over and over and over again. What's the probability that you roll a 3 on any given roll? 1/6. On average, then, how long do you think it's going to take you to see the first 3? Well, you're counting number of times until you see it. 6. Does that make sense? On average, it should take you 6 times to see a 3, because they come up a 1/6 of the time. Sometimes it'll be earlier, sometimes it'll be later, but on average, you'd expect to see a 3 every on the first 3 on the 6th floor. Right? We can do the same thing. We could do the same thing for the variance. Remember, if you wanted to do the variance in a similar way, remember last time we talked about that alternate form? I'm not going to do it this way. But we talked about if you want practice, you can do it this way. Okay? We said that was an alternate way to do it? No, we didn't talk about that?
We said it, but we're not going to do it.
I'm not going to do it. I'm just saying, if you wanted to do it the similar way you did with the mean, do it this way. That's what I'm telling you. If you want practice, I would try to do it this way. If you don't want practice, then ignore me. I don't care. It's not going to hurt me. Huh? Practice this sum with this thing using calculus ideas. It reinforces power series stuff. There's reasons why I'm saying this, but if you don't want to practice
Is it
it,
going to be on the test?
Say it.
Yes.
Well, he said there's reasons.
you're never done with any math when you go on to more math. No, that's not how it works. That's not how it works.
Advanced calc is the end.
Nope, that's not the end. Advanced calc might just be the beginning.
No.
You're never done with any math class until you just stop doing math, period. All the stuff always pops back up other places.
Well, looks like that's the day.
All right, so moment generating function, let's do it from this way instead. Because these moment generating functions for these distributions, yep, you're going to have to know them. Do you see this front cover? Yeah, you're going to memorize this front cover. For the next test, it's the left-hand side. The whole left-hand side.
We just have the book. We just have the book.
No! Because I said so.
Can I, yeah. We just get a formula sheet.
In the real world, some actuarial majors have to memorize those and they don't get them.
Well, I'm not. That's not my job. That would be my job. So I don't have to be like that.
If I get a tattoo on the inside of my eyelids.
Well, you go right ahead and do that.
Flip them up for everybody.
Can you guys see it?
I could give you a formula sheet. I choose not to.
So what I hear is you're going to make an exception for us.
Now, oh my! Your first page of your next exam is going to be that front cover, left side. You need to fill in blanks.
Oh.
Don't tell me that it's not that
So that
bad.
E to the TX is going to be.
That's how the definition of the moment generator. Well, you need to know the definition. Yes, because if I ask you to find a moment generating function using the definition, you're going to have to do it.
So that's what we would
So
put
this
for
is
the.
our definition.
No, you're going to no for this. If I ask you what is the moment generating function for the geometric distribution, it's the final answer we're going to get here in a second that you're just going to write down and fill in the blank.
Okay.
Okay.
That makes a lot more sense. Okay.
No, I'm not going to make you regenerate them every time. I literally want you to memorize that page.
Is that already printed there? Or we
Yes, it's already printed there.
I can't tell. It kind of looks like pencil.
I'm so glad it's Friday.
Preach it.
All right. Let's see how we can do this. Well, this is actually not that bad to get this moment generating function. I promise it's not that bad because I'm going to do the same thing, use the sum of geometric series like we did here. This has an x power, this has an x power, right?
Yep.
Right? Okay. So I'm going to rewrite it a little funky, but not too bad. I took out 1 power. I didn't take it out correctly. Not with an X.
That's clever.
Thank you.
I don't understand. I don't understand that.
You have to have both the same power.
Oh, you can just add 0.
Yep.
I always forget about that. I always forget about adding 0.
That's what I did.
At the very top, you're adding it.
I'm adding 0. Yeah, I'm cleverly adding
Yeah,
0.
you're cleverly adding 0. Why don't
You
we
know,
do that?
What's that? Oh.
You're bad at
Oh.
Obviously, yeah.
All right. So I wanted to bring in this e to the t inside the x minus 1, but I needed an x minus 1 power to pull it out, right? So I needed to add and subtract 1, which is why I got this extra 1 pulled out in front. And then again, to use our geometric series formula, which I erased, but that's exactly the same case that we had before, right? That's essentially r to the x, where x starts at 0. Right? So this will be shifted on me. Pe to the t over 1 minus e to the t times 1 minus p. What's that?
What's your pet?
Oh, the pet. I get you. I thought you said pen. I thought you said pen, and I was looking at what are you talking about? Peta. Enunciation matters. All right. There's the moment generating function. So if I want I'm not going to do it this way because I don't feel like to spend the time. If I wanted the variance, I would need to take the second derivative, right? Which is why I'm not going to bother doing it because it's going to be a quotient rule a couple of times. Plug in 0 and subtract off the mean squared. So how about I just tell you what the variance is? Does that sound like a plan?
Yeah, that sounds a lot better.
That's not so bad. So there's your variance for the geometric distribution.
How come it says that t has to be less than negative depth of 1?
Because from the theory for moment generating functions, you need to make sure that it exists somewhere other than 0. So that's what it's telling you that it's going to exist for. And it'll work as long as your t is less than natural log of whatever you need. Whatever it said it was. You just need to make sure you don't get a 0 in the denominator. Or a negative. That's why it needs to be that way. Yeah, Grace.
So that's the moment generating function for any geometric.
That is the, yes, once you know the p, you know the moment generating function for any geometric random variable.
So what was that for binomial?
What was that for binomial? Would you like to know?
Like, I don't want to work through it, write it down.
Yeah.
So for that, we're writing what the variance is?
Yeah, this is the variance for a geometric, yeah.
Okay.
That would be another blank that you would need to fill in the text.
So what would we write for this? So we'd write the e to the t over.
For the moment generating function? Yeah, for moment generating function, you would write that, yeah. For binomial?
But if we just want to memorize
That's what I'm saying. That is, yeah, you just memorize. I just want the answer, yeah. Yeah. Literally, there will be a sheet, your first page of your exam will have that. There will be blanks to fill in. I just want you to fill in the blanks. It'll say PMF, and you'll write the PMF. It'll say mean, you'll write the mean. But it's not hard. You just have to memorize it. For binomial, your moment generating function is 1 minus p plus pe to the t to the n. All right, let's talk about the negative binomial distribution. The negative binomial is an extension of the geometric. So the geometric was you run Bernoulli trials until you get to the first success. The negative binomial distribution is you're going to run binomial Bernoulli trials until you get to a fixed number of successes. Okay? So for this one, we're going to run a sequence of Bernoulli trials is run until, we'll call it the kth success is observed. So instead of the first success, it'll be the kth success. And then x is going to count the number of trials. Well, I'm going to leave it as k now, but the book uses r. It doesn't really matter. It's just a counter. It's just a constant. It doesn't matter what it is. What's the smallest value x can take on? Sure, it's 2. In terms of this scenario, what's the smallest value that x can take on? you're going to run trials until you get to the kth success, what's the smallest that x can be?
Okay.
K.
I
Yeah.
nailed it.
It's K. You're going to run success. You're going to run trials until K successes is found, right? The smallest it can be is K. You can't get K successes if you run K minus 2 trials, right? The smallest X can be. So the support here will be K, K plus 1, K plus 2, and so on down the line. So if you have X, capital X equals little x trials are necessary. How many successes and how many failures did we have? Oops. Well, the first part of that question is easy. If you're looking for K successes, how many successes happen? K. Yay. Okay. If you ran X trials and you know that K of them are successes, how many are failures? X minus K. Good. Okay, cool. So there are K successes, N minus K failures. X, sorry, thank you. Little x. Big X is the name for the random variable, and little x is the actual number that we're using. I know it gets confusing, but
I like it because
I know.
it's not like big A and little.
It's like, what is she?
No, you
Sure it is. Watch. Big A, little a. See? They were different colors. It's true. All right. So let's think about how we would fill in. Like, think about slots. We've got X slots we have to fill. Now I'll put one more here. Okay. But what does the last, what we're going to do, remember, we're going to run the trials until we hit the kth success. Once we hit the kth success, we stop. So what has to be in the last slot? Yeah, a success, right? It has to be the last success, correct? And we use the probability of success to be P here, correct? Right? The last slot has to be a success. Correct? So what goes in the other X minus 1 slots? Various P's and 1 minus P's, right? How many P's and how many 1 minus P's? K minus 1 P's and X minus K 1 minus P's, right? I still have to have that many failures, right? I didn't use a failure up, right? There has to be K minus 1 P's, X minus K 1 minus P's, right? These are all independent. So if you had several P's and then followed by several 1 minus P's, how would you calculate the probability? They're all independent, one after the other, so how would you calculate the probability? You would multiply them, right? So we have to have a P to the K minus 1, a 1 minus P to the X minus K, right? K minus 1 successes, X minus K failures, times an extra P on the end, right? Now, notice that this would be, the way I've got this written would be, the first K minus 1 are successes, the next X minus K are failures, and then the last one was a success, right? Is that the only way to get k minus 1 successes in those first trials? No, there's different rearrangements, right? How many choices give me the same thing? Well, how many slots are we filling? X minus 1, right? And how many things are we placing? K minus 1 successes, right? So in front here, we'll have an X minus 1 choose K minus 1. There's your PMF for a negative binomial. Now, of course, you can combine your p's together and just write it as p to the k here, right? Yep, so you just write it as p to the k. This is the part that makes sense, I think, here, right? When you write it as p to the k, 1 minus p to the x minus k, you've got k successes and x minus k failures, right? It makes sense that looks like exactly like the binomial did, isn't it? All right? What's different is that the last slot had to be a success, right? So that's why this choosing coefficient, this binomial coefficient in front is different. I don't have x choices and k choices anymore, right? I've taken one of the choices away. I've said the last slot had to be filled by a success. So there's x minus 1 choices left, k minus 1, or x minus 1 possibilities left, k minus 1 choices left. Okay? So this is your PMF for the negative binomial. We'll write down the mean and the variance next time. They make sense though, because they look a lot like the geometric. The negative binomial, the geometric is a special case of the negative binomial. This is where k equals 1. We'll do more of this on Monday. Enjoy.
The homework assignment, when is it due?
It's due Wednesday.
Wednesday.
Out of the textbook, you would do 2.4-18 and 20. Same section. 2.4-20. And then you've got out of the chapter, the section 19 handout is 19.3.
19.3.
19.6.
19.6.
19.16.
19.16.
And 19.20.
19.20.
Out of the section 20 handout,
Yep.
it's 2010, 2012,
2012.
and 2019.
2019.
And out of the 27 handout, don't sigh at me. It's 27.3, 27.6, and 27.7.
27.6.
27.7.
Jeez Louise, Dr. Joe.
There's 12 problems.
That feels like a lot of problems, though.